So welcome, and let's have a look at this. This is a conceptual question again. Let's get our pen up and running. So let's have a look. I want to have pen. Let's get a different color because I want blue. Okay, so let's have a look. A pickup truck accelerates a car. So here's the pickup truck and here's the car. Accelerates the car. Oh, sorry, I'm one out. A pickup truck. Here's the pickup truck and here's the car. And it pushes the car at a constant, so V equals 50 miles per hour along a straight and level section of 275. Compare the force of the pickup truck, that's force pickup on car, with the force of the car on the pickup. Force car on pickup. So I'm going to open up the voting system. If you didn't get a clicker, come and get one. We've got about 8 left. And give me your thoughts on this. What do you think? Nice conceptual question. Let's put my pickup truck. So I've got 12 people. I've got 25 clickers out. Who's not got a clicker? I've only got 25 people here today. Who's not got a clicker? Come on. Oh, that's right. You're not there. So let's have a look at 23. That's very good. Let's hold it there. Let's. I give the people who just got them just a quick chance to. You just turn it on and you go click. Okay. So one more. I'll stop at 30. Boom. There we go. Okay. So let's look at this. So most people are saying B, a couple of people saying A, a couple of people saying C. So let's have a look at this. So first of all, on my diagram, where is the force of the pickup on the car? Well, it's going to be pushing on the car in that direction. That's my force of pickup on car. And here's my force of my car on pickup. It's kind of like, action-reaction pair. You change the names around, opposite directions. And they're Newton's third law says they're equal and opposite. So it's going to be B, isn't it? Now, okay, that's fair enough. Just apply Newton's third law because it's a law. So, what about this guy? Pickup truck accelerates. So now we have A is equal to, I don't know what it is, but it's in that direction. It's not equal to 0. And let's have a look. Straight and level section of 275. Here's my pickup truck. Here's my car. So compare the force of the pickup on the car with the force of the car on the pickup. And the difference, of course, always compare and contrast. The difference is before it was constant speed. And now it's not constant speed. Before there was no acceleration, and now there is an acceleration. So how do these two forces balance out now? How do these two forces compare now? So let's have a look. I'm gonna actually pause the recording just for a. So let's freeze this. Let's look at our graph. Oh, a bit more. There's even a D down there. Somebody was So, but most people are saying C, which is the force of the pickup on the car is more than the force of the car on the pickup. And I want you to, well, okay, that's wrong. So I want you to have another go at it. Vote again. I'll let you not see. They're not. The force of the car on the pickup is not greater than the force of the pickup on the car. It's not. I'll explain why in a minute, but it's not. Try and think why it's not. I got 17 votes. Let's go for just a minute. Let's see. And while you're doing that, I'm going to come along here and I'm going to go to eraser. So how are we doing? Get rid of that and we'll do that again. So 25, let's stop. Let's have a look at our score now. So now people are saying B. So yes, and that is the right answer. So why is that the right answer? Can I justify it? So yes. Let's have a look at it. Let me get my pen back. Oh, sorry. Let me get my pen back. So let's have a look. Pointer options. Pen. So let's draw this nice and big. So here's our pickup. And here's our car. It doesn't matter about the size. I just want to see. And the force of the pickup on car is there. And the force of the car on the pickup is there. And according to Newton's second law, they're an action-reaction pair. And so they are equal and opposite. So B must be the right answer because of Newton's second law. But if that's the case, how do we get an acceleration? How do we get an acceleration? Yes.
Difference in mass.
No, actually no. You could have equal size objects and this would still work. Think in terms of there is friction involved.
The wheel to the ground.
And there is the wheel to the ground involved. So acceleration is caused by, when I say the sum of the forces equals ma, I'm being really slack, aren't I? I'm not really putting down, what I really mean. I mean, well, that's F net, isn't it? That's what the sum of the forces means, the atom vectorial in F net. But it's not just that. It is what kind of forces. Remember we used an example last time where you could push on your car in one position and you'd get an acceleration, and you could push on your car in the other position and you would not get an acceleration. Yes, it needs to be external. And the problem with these two is that they're kind of like inside the system. So what do I mean by the system? Let's turn sorry, I'm just a little bit slow today, so let's go to green. So it is this system that accelerates. It's both cars together. And these are not external forces to the system. They're internal forces. It's like pushing on your own dashboard. Doesn't do you much good. What we have is we have the force of the air on the car. That's the wind resistance. And of course we have the force of the car on the air. And that's pushing the air out of the way. And then back here, we have, I'm going to draw it down here, even though it's to do with the wheels. We have the force of the road on the truck, and we have the force of the truck on the road. And what I mean by that is the tyres pushing backwards and the road pushing forwards, that kind of thing. Yeah. So I actually have 3 action-reaction pairs, and they're all within themselves equal to each other. So action-reaction pairs are always equal to each other. But there's no law says that this action-reaction pair has to be the same size as that action-reaction pair. There's no law says that every action-reaction pair in the universe has to be the same. So I get acceleration when there's an imbalance in my net external forces. So let's get another color. Let's go to red. So what I have now, did it go? No, it stayed at green. I don't care. I'm going to do it. I'm going to be. The more I practice, the easier it will get. So you have, which are the external forces? It's that guy because it's pushing on the system, and it's that guy because it's pushing on the system. They're the two external forces. And if these two are in balance, so if FR on T equals FA on C, we get coasting. Constant speed. Because it doesn't accelerate, because there's no net external force. If FR on T, if the back one is bigger than the front one, what do you think happens? I get acceleration in that direction, and the velocity is in that direction. So I speed up, don't I? And if I have FR on the truck is less than the force of the air on the car, then I get acceleration again, but it's in the opposite direction, yeah? So I say this is acceleration, and this is the velocity, so I get slowed down. Remember that? When the acceleration is in the opposite direction to the velocity, you slow down. When the acceleration is in the same direction as the velocity, you speed up. So if the air resistance is stronger than the driving force of my tires, I slow down. If the air resistance is less than the driving force of my tires, I speed up. And if they're balanced. So this is a classic. In all my time teaching, I used to run the TA program for the physics department at USF, did it for about 6-7 years. And one of the things I do is when I got new graduate students in from all over the world, these are smart people, these are from, got degrees in physics, some of them master's degrees. And I would give a test that included this question. And I would say, even after all that training, about a third got this. And the other 2/3 knew there was a problem. They felt uncomfortable with the answer. They were saying it was equal, and they felt uncomfortable with the answer because it's really bringing you into conflict over two things. F equals ma, and the sum of the forces equals 0. It's like, man, they're inconsistent with each other because they apply to different things. F equals ma is for the external forces. Action-reaction pair is for an action-reaction pair, which in this case is internal. Occasionally there'll be an undergraduate who gets it first time, and it's really excellent when they do. To some extent, I think there's a bit of personality involved. The law's the law, and they apply it, and other people make exceptions. I know I did. I made, this is a special case. And, laws don't have special cases, So, but there was an alarm bell. I remember the first time I did this, I got it wrong. And I kind of knew I was getting it wrong. And it was one of those things where I voted, even though I kind of knew I was walking off a cliff, but I didn't know what else to do because I was being overwhelmed by F equals ma. But I knew that, I was overwhelmed by action-reaction pair. But I knew that, there was issues.
So
And
why is the truck not an external force on the car? Why are they?
No, they are. But the fact of the matter is that they're not an external force for this system. Okay? I mean, the force of the car on the truck is an action-reaction pair with the force of the truck on the car. Agreed, yes?
Yeah.
Now, are they... So is... For acceleration, you look at external forces. So for the truck, the two external forces are this guy and that guy.
Yeah,
And
I'm
then
just wondering why we don't think of the truck pushing the car as an external force.
on which one?
What do you mean?
Well, it's got to be an external force on something.
On the car?
Oh, on the car. So on the car it is. It's an external force. There's the force of the pickup truck on the car, and there's the force of those two. They're not equal. This thing accelerates. This thing accelerates. The fact is they accelerate to the same extent. Yeah. So yeah, that can be an external force for the car, and you've got to compare it for F equals ma with the external force coming from the air. The problem is that people say, oh, there's my external force for the system, and they cancel out. And those two together are not the external force on the car, because this one's got nothing to do with the car. I mean, it's not an external force for it. It's got something to do with it, but it's not an external force for it. So it's that parsing. It's recognizing there are action-reaction pairs. It's recognizing there's more forces than you are told about. And then it's recognizing that F equals ma, we have to look at the external forces. Okay. And, this is an external force for the car, but that is not part of the F equals ma. Yeah? Yeah? Cool? Okay, well, anyway. So you'll see that, and, try and live with it, and try and recognize the fact that the problems require analysis. They're not just, it's never going to be plug and chug. There's always going to be some kind of analysis in this. So let's talk about inertia and mass and weight. And this is something that people struggle with. If I pick up one of those big black metal things in the lab, what is it called? Don't say Ricky. It's not called Ricky. But what is it called? If I go to the lab and I get one of those big, they're made out of lead. What do I call it?
Lead weight.
Oh, lead weight. It is. What units does it come in? Kilograms. It's a lead mass. You can call it a lead weight if you're going to tell me how many newtons it is, because weight is a force and it's measured in newtons. You can call me it's a mass when you tell me how many kilograms it is. And this is where, as scientists, we inherit these things. I think I told you about the rulers and how we have, in many cases, we have rulers that are numbered in centimeters, but the smallest division is millimeters, so we call it a millimeter ruler, but the numbers are in centimeters. It's completely illogical, but we kind of live with it, yeah? If you go to the massing machines in the lab, it will say the weight 60 grams. And grams is a mass. So it's kind of like our own technology is not clear on this. It's like, as an engineer, you'll watch television, and every time there's a news program, you'll pull your hair out, because they misspeak about science all the time, and it just perpetuates these problems. It's just like the news is reinforcing incorrect ideas. Then I saw it on the news. It's going to be so and so. It's not that and it's not misinformation. they're doing their best. They're just misnaming things very often. So as scientists, you kind of learn to be, language is precise. So a mass is in kilograms. Mass is a mysterious thing. It is not how many atoms are there. It's not how hard gravity pulls on it. It is, and I'll tell you how mysterious it is, if you take that mass and you apply an external force to it, and you look at its acceleration, as you apply more force, you will get more acceleration. And if you plot the graph, you get a straight line, and that slope is the mass. It's as abstract as that. The weight is measured in newtons. And the weight depends entirely on where you are located. If I go into interstellar space, every mass has 0 weight. As long as I don't put a lot of masses there. It's got to be isolated. But I can take my 1 kilogram mass and take it into interstellar space, and it will have still 1 kilogram of mass, but it will have no weight because there's no gravity to speak of pulling on it. Even if I only go to the moon and I take my kilogram to the moon, it would have a weight of 1.6 newtons rather than 10 newtons. Because it's a sixth the pull of gravity there. So weight is completely kind of arbitrary. It depends on your location. It's a very flexible thing. We tend to only talk about the surface of the Earth, and we tend to only talk about it being a constant value. We don't go too high. We don't go into the Earth. In which, if we go into the Earth, then the weight gets less. We don't do any of that. We just say it's always 10. Question or comment?
So the weight in the water is the same, but that's like a buoyancy force, right?
Oh.
But it's still the same.
So in buoyancy, we'll play with the weight of water and the weight of a block. We'll talk about those forces, yes. So I don't want to talk about them now, though.
And the number is the same, sort of.
The
right?
number.
Yeah,
What do you mean?
like the weight number, like you still weigh the same in water.
So the weight of the object is the weight of the object.
Right.
The weight of the displaced water is the weight of the displaced water. People then talk about buoyancy and buoyant force. And they're talking about combinations of those. And we'll get to that in like 5 chapters. So, as I say, we'll get to that in about 5 chapters. So, one of these is constant throughout the universe, and the other one depends upon my location. And one of these directly affects my motion, my acceleration, under all circumstances in a very controlled way. So what Galileo realized was that the more mass you had, he didn't know about this graph, he just knew that the more mass you had, the more reluctant you were to accelerate. So what Galileo reckoned was that mass is proportional to reluctance to accelerate.
Reluctance.
Yeah, reluctance. Yeah, how reluctant you are to accelerate. And that was proportional to your mass. So the more mass, where's my pen gone? The more mass, the more inertia, the less acceleration for a given force. So that's inertia. So he kind of recognized this thing which is not obvious. And it was a very insightful thing. Recognize that if your equation includes mass and not g, then that thing will be the same all over the universe. Whereas if your equation includes mass multiplied by g, which is weight, then that thing is location dependent. So let me give you an example. If I take a box into space away from the Earth, I'll be able to hold this big heavy box with one hand. Agreed? Because I'm as strong as I was on the Earth, and this thing weighs much less than it does on the Earth. Because the weight is equal to mg. As g gets less, the weight gets less. For me to spin that box requires a thing called centripetal acceleration, which depends only on mass. The mass has not changed. So we end up with these ironic situations where you can hold a really massive object at ease in space, but you can't rotate it very easily. And that just seems completely counterintuitive, because some things depend upon weight and some things depend upon mass. So we can't just say, oh, everything's easier in space, you know, like, oh, I can just take the space shuttle and just spin it. I might be able to, I might, so just watch out for that. It's like, again, building up your physics intuition. So mass and weight. So weight is a force. weight's magnitude changes depending upon the gravitational field strength at that location. At the Earth's surface, the gravitational field strength is 10 newtons for every kilogram. This means that 1 kilogram weight, whoa, wash my mouth out with soap and water. 1 kilogram mass has a weight of 10 newtons. You can see how ingrained it is in all of us. I like people to have a feel for the size of things. An apple, remember apple landed on Newton's head and he said, gravity. Did you hear that story?
No.
The story is Newton was in his orchard, apple fell on his head and he invented gravity. There is actually an apple tree in Newton's garden. And when they looked at the rootstock, it was really old. The apple tree had been there for a long, long time. So it's not impossible that it happened, but I think he was thinking a lot more diligently about forces and objects before the apple hit him. But Newton's connected with the apple. And I think there's some story that he actually promoted this story as he got older. As he got older, he had a blossoming in his social graces, and he would tell anecdotes about his life. And that was apparently one of the stories he told.
That's actually how I first learned it.
Yeah, most people do. But I'd like you to have a sense. I'd like you to remember that 1 Newton is about the weight of 1 apple on the surface of the Earth. So you want to know how big a Newton is? Imagine holding an apple. Yes, there are big apples and small apples. Just pick one. Pick one and live with it. It's okay. If you took the same kilogram to the moon, it would have a weight. So on the moon, the pull of gravity is less, so there it's only 1.6 newtons for every kilogram, so 1 kilogram would only have 1.6 newtons as weight. And the key relationship is the vector force, the weight, the force due to gravity, is equal to mass times this little g. And this is, you probably learned it was 9.8. I prefer to call it 10 because it's mathematically a lot easier. And you were probably taught that F is equal to mg, and g was 9.8 meters per second squared. And that's not untrue. That is a correct statement, but it's not really what it's about. What it's about is that the Earth sends out a whole bunch of, it establishes a gravitational field. And that gravitational field falls off with distance. And the gravitational field is the force that a 1 kilogram mass would feel at that position. And so G is really measured in newtons. How many newtons of force would you feel per kilogram? And it's 10, I like to call it 10 newtons per kilogram. It points towards the big mass. So it's not that it's wrong, but try and disconnect from F equals ma, and G is just a special kind of A, and try and connect with F equals mg, and G is the gravitational field strength. And you can tell people will want to put a negative sign in front of this, whether or not, no matter which direction the thing's pointing. And that's okay, but you've got to know why you're putting a negative sign there. And so it's just watch out for that. And the reason why I'm dead keen on this is because in electrical engineering, in physics 2, you're going to find that Fe is equal to Q times E, where this E is the electric field strength, and that is measured in newtons per coulomb. And if you get this idea down for gravity, you will get that idea very easily for electricity. So just try and break that G connected with acceleration and connect it with the gravitational field strength. Let's get on and talk about equilibrium. Equilibrium and non-equilibrium. So, if the sum of the net external forces, so we'll say F net ext, let's learn from our mistakes, is equal to the sum of the F external forces, and that equals 0. We are in equilibrium. Or if F net ext, which equals the sum of all the external forces, equals not 0, then does not equal 0. We are in non-equilibrium. So we're in one or the other. And by the way, if that's the case, it equals ma. So equilibrium is to do with, is your net force 0 or is your net force non-zero? Because we have equilibrium along axes, you could be in equilibrium along your x-axis but not in equilibrium along your y-axis. That's quite allowed. They don't affect each other. So, and this leads us to statics and dynamics. When you've got equilibrium, you've got statics, and when you've got non-equilibrium, you've got dynamics. And their entire courses, if you go to engineering school and you're doing anything to do with mechanics, you'll do statics and dynamics. So here's a typical example. We start talking about the traffic light problem. And the reason is, it's a thing that everybody's kind of seen, although now it's changing. There was a time when we'd string up all our traffic lights using guy wires, and now we use those big kind of like pipes. So I'll have to change my analogy at some point. But when you get a mast that's hanging from a couple of different support mechanisms, then we can do calculations on it and figure stuff out. I'm sorry?
Are those angles at 40?
You got to speak up, sorry.
Is that 40 and 30 angles?
Yes, they're 40 and 30 angles, yes. And this is in kilograms. So, this is the typical scenario. And there's several ways of doing this. First thing, this is a traffic light. It's tied to a couple of lampposts using wire. It's a calm day. There's no wind. Is this thing in equilibrium? Yeah, this mass is not accelerating anywhere. It's just hanging there. So that's the assumption. Yeah, we all know when we talk about traffic light problem, we're not talking about a traffic light on a blustery day. We're talking about this situation, nice and somewhat idealized. And there's two ways I can do this. I can do this using the slow and steady way, or I can use it doing the fast way. And most people prefer the slow and steady way, but after a while they get to the stage where they recognize that the fast way is better. First warning, if I were you, I would never rely upon my diagrams, because I am not going to make the angles correct. Because if I did, you could just draw a vector diagram and measure your answer with a ruler. So I'm never going to use a scale diagram. I'm going to give you schematic diagrams. If I give you a diagram at all, I might not even give you a diagram. So get used to drawing your own diagrams. But secondly, if you draw a better diagram, you will catch errors. If you draw everything at 45 degrees, there's no big angle and there's no small angle. So when you start trying to propagate angles around your diagram, they're all about the same size. So you can't tell, is it the 30 or is it the 60? You know that 30 and 60 go together and make a right angle, but you don't know which is which. So the chances that you will put down the 30 rather than the 60 is much more significant. So what I learned to do when I was, going through this, and I struggled when I went through it, I think the same way that a lot of people struggle. What you learn to do is you learn to try and avoid errors. And so what I try to do is I try to make my diagrams reasonably good. I'd even go to the stage and say, if you're not comfortable doing diagrams, by all means get yourself a little protractor and then draw them at the right size. So I look at this and I go, that is a 30. Oops. And I'm going to try and draw it a certain length. I don't know how long it is, but I know that's 30 degrees. And I'm going to come across here, and this is not quite 45, but it's not as low as 30. And that's going to be 40 degrees. And I'm going to call this T right because it's pointing to the right, and this is T left because it's pointing to the left. And then I have another force down here, and I'm not going to put the 3 kilograms there. I know we're on the Earth, so I'm going to put down 30 newtons.
30 or just 3?
If the mass is 3, when I put a number inside a box, it's a mass, because weights are forces, so they have directions. So weights go on arrows. So there's my shorthand. Okay, I'm learning to put things in shorthand. So there's my simpler diagram, and the kind of the brute force way is you say I want to use Newton's laws. I'm going to divide this up into horizontal and vertical. So let's go across here. And I'm going to come across and I'm going to say, I'm sorry, I need to use different colors. And I just want them to be, let's do green. I just want them to be as clear as possible. Okay? So what I do is I say the sum of the forces horizontal equals 0. So I got to break this up into my components. And I go like that. And I don't know where the arrow on the T left and T right should be. I'm just, arbitrarily picking an original length, and I'm arbitrarily drawing these arrows. I know they should be about the same length, but, And then I write an expression for this. This will be TR cosine or sine 30. Cosine 30. And you've got to get to the stage where you're just comfortable and quick doing that. Is this pointing to the right or pointing to the left? So call it a positive. I'm going to call that the negative direction. On this side, I have T left. Is it a cosine or a sine of the 40? Cosine 40. And is it pointing to the right or to the left? So call it a negative. So over here, I say T right cosine 30 positive added to minus T left cosine 40 is equal to 0. I just do what I said I was going to do. Sum of the forces equals 0. I don't rearrange. I don't do anything like that. I just write down those things. Now, some people like to leave their cosines and sines till the end to change. Other people like to get into numbers straight away. If you get numbers, don't round too much because this is going to round and round and round. So I'm going to turn around and say, first of all, I'm checking them in degrees, and these little calculators, you can see it says DEG. And then I turn around and say, so cosine 30, I should know this, shouldn't I? It comes up so often. So this is going to be 0.8660. I'm doing 4 decimal places, TR. And that's going to be added to minus, I'm going to go cosine of 40 equals 0.7660 T left is equal to 0.
Does that H stand for horizontal?
Yes, that H stands for horizontal. Now, I didn't actually read what the question wants me to find out, and the question wants me to find out what T left is. So it's T left that I want. I'm going to try and really emphasize that to myself because I don't want to find the wrong thing. It's not the end of the world, but it just slows me down a bit. And if you want to end up, well, first of all, can we solve for T left in this equation?
Yeah.
I don't think so. We don't have TR, so we can't solve for it. So we need to do something else. And we tried using T horizontal, force horizontal, so we're going to use force vertical. So let's just go through it step by step. So I'm going to come along here. I'm going to go to there. I'm going to go to a, let's do red down here. No, let's do that red, that other red. So now I'm breaking this up, and I'm going, that's vertical, and I'm going here, and that's vertical, and then this is going to be TR, well, sine 30, isn't it? And it's in a positive direction. And this guy, I'm going to do it all the way up here, is T left, sine 40. And that's also positive. So just look at those trig and make sure you know where those come from. I could have used cosine of 60 on the right-hand one, and I could have used cosine of 50 on the left-hand one. It's the same. Cosine 50 is like sine 40. So it makes no difference. I can't say cosine 40 on the left-hand one because it's wrong. I can use either one, but I got to put a correct statement down. So then I say, well, the sum of the forces vertically is equal to, well, it's not accelerating vertically either, so I'll put that down. That's 0. And then I just do what I said. So I say, okay, that's TL sine 40. That's a positive. Added to TR sine 30. That's a positive. Added to, I got one more force. What's that force?
30.
And because it's pointing downwards, it's a minus 30 newtons. Okay. 2 equations, 2 unknowns. I have a solution. But I got to get the solution. So again, some people like to leave their sines and cosine numbers in there, but other people don't. So we're going to do sine 40, and that's going to be, so this is going to be plus 0.6428 TL, and this is going to be sine 30. Oh, I think I know sine 30. What is sine 30? 0.5 TR. I'm going to say it equals 30 because that's where I'm going to go in the end. I take the 30 to the other side. So now I need to do some substitution. And what you learn is if you want to end up with TL, on one of these equations, isolate TR. So you can substitute in. And so what I would do is I would come along here and I would say, okay, I'm going to substitute. I'm going to say TR is equal to, take that to the other side, plus 0.7660 TL divided by 0.8660. So let's just double check on that. I wanted TR by itself. I moved my T left to the other side. It became a positive. And then I divided by my coefficient. So, and again, some people are happy to leave it, and other people want it to be just a single number.
What about the 30?
I'm using that green equation. You see this guy? It's going like that. Yeah. Should have gone back to green, shouldn't I? That's what I'm using. So then I say 0.766 divided by 0.866, and that's going to be 8845. Let's keep to 4 TL. And now what I do is I substitute that into here. So I get 0.6428 TL plus 0.5 times 0.8845 TL. So I substituted in for that TR. And the substitution is that whole thing. It's 0.8845 TL equals 0. So let's have a look. 0.6428 TL added to, well, it's just half of that, so 0.442, I'm going to say 3 TL is equal to 0. Add these is equal to 30. Whoa. I'm sorry, just notice I said 0 here, it should have been 30. So add these two guys together, 11, carry 1, 2 and 2 makes 4 and 1 makes 5, 4 and 4 is 8, 4 and 6 is 10, 1.0 TL is equal to 30, so TL is equal to 30 over 1.0851, which equals, this is going to be 30 divided by 1.0851 equals 27.65. I put the units in, don't want to lose points because I don't use units, and I put it in a box.
What are the units? Just,
Well, what are you trying to find? This is the wonder of the SI system. If I'm trying to find a force, and I've used SI units, the answer's in force. I know sometimes you're encouraged to put down the units and cancel, and that's not bad, but that's to kind of prove to you that you did all the layout right and things work out. But I think when you get to a stage where we fly through things, so I've got confidence that if I use SI units, forces come out in newtons, masses come out in kilograms, etc. Yes?
why'd you use the horizontal TR and TL to get what TR equals?
No, I just have two equations. Two equations that contain two unknowns. So mathematically, I can pick either one of them.
Because the unknown is the same value.
Because TL is the same in both equations. So I choose the easiest, the simplest, the shortest one to get the value to substitute. Yes?
So that difference in just 10 degrees makes it hold up most of the weight.
I'm really glad you asked that question. Please, I'm really glad you asked that question because so what you are implying is that if 27.6 newtons is held up by T left, then there's only 2.4 newtons in T right. Yes? Can you just do me a favour? How many people would agree with this? I mean, I'm kind of setting an alarm bell, but can you just plug in? So the question is, given that T left is 27.65, then that means that T right is going to be 30 minus 27.65. How many people think that's right? How many people think that's wrong? Because I'm going to ask you why if it's either answer. So give me an answer. What do you think?
What we're playing for.
Just give me an answer. What do you think?
What are we supposed
A
to
is right and B is wrong.
Oh, sorry.
What are we supposed
A
to
is
play?
yes. A is that T right is going to be 30 minus 27.6. I'm just curious. So do you think the sum of your two upwards forces add to 30 because the downwards force is 30? That's the key question. If you think yes, put A. If you think no, put B.
But is the object like stable? Like
It's equilibrium. Yes. Yeah, equilibrium. So what do you think? You know, these things, it's not accelerating anywhere, so it's in equilibrium. So do I find T right, by simply taking T left away from the weight? So what do you think? This is a very key question. I'm so glad you asked this question. I'm so glad you made that statement. Got 20 people. Let's get a few more people. I'm really curious to see what you say. I'm going to stop it now. Let's see what people say. So most people say that. Very interesting. So the answer actually is that
No,
it's not.
because it would be the opposite sides that have to add to 30, right?
What do you mean by opposite sides?
The opposite to the 40 and the 30, the ones that are vertical.
Yes.
Because those are at an angle,
Yes.
not straight down.
So this is where you know, visualization becomes really important. The statement that the downwards forces must balance the upwards forces sounds just so great. And you know, yes, if I'm talking about that, that's true. The upwards component of T left and the upwards component of TR do balance the 30. But this force and that force are not in the same line as the 30. So they're numerically not going to equal each other. So I am going to get probably 30, 27 here. I'll probably get 29 there. And there's going to be 30 here because it's more. It's a vectorial addition rather than an arithmetic addition. If you want to add using just numbers, you've got to be on a straight line. And that raises that thing you raised there is that whole thing about why do we work in components? Because we want to be able to do sums like that, and the only way we can do sums like that is if we're on a straight line. Very good question.
If they were both 45 degrees angles and both would be 30 newtons?
If they were both 45, I don't know if it'd be 30, but they'd be equal to each other. Yes, if they were the same angle, they'd be equal to each other. If you ever done any kind of gymnastics, if you hang from a bar,
If it were 60 degrees, they would be equal.
yeah, if there was 60 degrees. If you hang from a bar, they'd be it's hard. But if you try and raise yourself, if you Olympics, people are doing that. They're trying to do that thing. It's incredibly hard to kind of hold yourself with your arms out like that because the forces in that direction have to have a component which makes half your weight, and that's really hard. So yeah, very good thing you hit on that. So what I want to do now is I want to do this question again quickly. So I want to show you another way of doing it. I might not be able to finish it. In fact, what I'm going to do is I'm going to stop. I'm going to do a 5-minute break, and then we are going to and then we're going to come back and I'll show you what I think of as